In this video, we'll cover our first reactions with a carboxylic acid. So a carboxylic acid will be one of the reagents. And in this video, we'll talk about Fischer esterification. So Fischer is just the name of the chemist that discovered and used this type of reaction. And then esterification means that we are going to take a carboxylic acid and produce an ester. So we'll get a slightly different functional group in the product. And so generally, this reaction starts with a carboxylic acid. So here's our carboxylic acid functional group. This reaction requires an acid and then some alcohol solvent. And which alcohol solvent you use will influence the product that you obtain. So we have carboxylic acid, acidic alcohol solvent, so this is acid catalyzed, and this forms an ester, so that's why it's called esterification. And an ester is a functional group where we still have a carbon double bonded to one oxygen, bonded to another, and then that oxygen is bonded to a carbon chain. And so that carbon chain comes from the alcohol. So different alcohols will produce different esters. So here's an example. We'll start with benzoic acid. So this is our carboxylic acid. We'll have some acid present, sulfuric acid present in methanol. So this is our solvent, which implies that's in large excess. And when we go through the mechanism, you'll see that this reaction is reversible, and so having more starting material, having a higher concentration of starting material, including the solvent, will promote the forward reaction. So the product here, we have all of the carbon atoms from the carboxylic acid in the same bonding pattern. So here's all the carbon atoms. Both of the oxygens are still present. And then this oxygen that was the OH group is now bonded to a CH3, a methyl group. So if we just add in our electrons, there's our final product there. Okay, so there's our general scheme and example, and then we will show the mechanism for this example here. Instead of drawing out the phenyl ring, we'll abbreviate that with a pH, capital P, lowercase h, that represents phenyl. So we have our starting material, carboxylic acid. Now, this occurs in acidic conditions. And so the first step is to activate the carbonyl. We do that when there is an acid present. And so if we have sulfuric acid and methanol present, then in our mechanism, we will be using methanol and protonated methanol. So the sulfuric acid will protonate the solvent molecules, so we'll have both neutral and protonated solvent present. And so for the first step, when we are showing that the carbonyl oxygen gets protonated, that will be shown with protonated methanol, because this is a better proton donor. Let's just be a little bit more explicit. So all of this here implies that we have CH3, OH, and CH3O will draw out these bonds. OH2, positively charged, oxygen, both of these are present. Okay, so we'll use both of them throughout the mechanism. For the first step, when we are protonating the carbonyl oxygen, we use protonated methanol because that is a better proton donor. All right, so we activate the carbonyl. So we have a even more electrophilic carbonyl carbon. So that carbon is susceptible to nucleophilic addition. So in our nucleophilic addition step, we will be adding a solvent molecule, and neutral solvent, so not protonated, is a better nucleophile than protonated because this oxygen is more willing to give away electrons if it's not already sharing a pair with an additional proton. So we show our nucleophilic addition step. I break the pi bond. So this new bond to the positively charged oxygen is what is changing in this step. So we have that new carbon to oxygen bond. We have a positively charged oxygen here. We can do a proton transfer to neutralize it. So that's what we will do in this next step. We are removing a proton from that oxygen. And so in this step, again, neutral solvent is a better base. In this case, it's acting as a base because it's taking a proton. So we use neutral solvent there. And that will produce our neutral tetrahedral intermediate. In our final product, we have a pi bond to that carbon. So that carbon's bonded to two oxygens in that phenyl ring. Well, we can't break, it's difficult to break a carbon to carbon bond, so we won't be breaking the carbon to phenyl bond, as we can see that's present in the product as well. But we do need to break a carbon to oxygen bond, one of the carbon to OH group bonds. That will allow us to then generate a double bond between carbon and another oxygen. So we need to lose that OH group, one of the OH groups. We're in acidic conditions, and so OH on its own is not a good leaving group. So just looking at an OH right here, not a great leaving group, especially in acidic conditions. But if we pronate that oxygen, that will generate a better leaving group. And so we will protonate this oxygen here, and since we are taking a proton from another molecule, we will use protonated solvent. This is a better proton donor. So one of the OH groups gains a hydrogen from protonated solvent, and then that oxygen to hydrogen bond from the solvent will break. So copying over everything that stays the same first. Now we have two bonds to this oxygen. We have generated a good leaving group. We've generated a good leaving group, so the leaving group will do what its name implies. It will leave. This generates, I don't know if you can see Lucy's tail in the corner. She's joined us. So this generates an open shell carbon. We have an OH group and an OCH3. We've lost the water, so now we have an open shell carbon here. Now this open shell carbon can exist with a closed shell if we show resonance. I'll use a different color here to show this resonance. The OH group in one resonance structure can share its non-bonding electrons. So now instead of drawing an equilibrium arrow, I've drawn a resonance arrow. This generates a closed shell carbon. We do have a positively charged oxygen. But this resonance structure is more stable. But now, if you look at this molecule, and I'll scroll up and look at our desired product, the only difference between this molecule and our desired product is that proton bonded to that double bonded oxygen. So our last step here is to remove that proton, and we can do that with a neutral solvent molecule because this is a better proton acceptor than the protonated solvent. So that will take the proton from the oxygen, and we've generated our final product. Where we have an ester bonded to a phenyl ring with a CH3 group bonded to that oxygen. So this is the complete mechanism. We work in acidic conditions, so everything will either be positive or neutral. Start with activating the carbonyl by protonating the carbonyl oxygen. Then we do nucleophilic addition with the neutral solvent, proton transfer, and then we protonate an OH group to generate a good leaving group. That leaving group will leave, and one of the resonance structures of that next molecule has a double bond between oxygen and carbon. And when that double bond exists, we can see that that hydrogen bonded to that double bonded oxygen can be removed by a neutral solvent molecule, and we get our final product. So let's look just a little bit more detail into this resonance structures that we've drawn. We'll draw all of the major resonance structures for that molecule, or for that intermediate. But as it stands here, this is the complete mechanism for the Fischer esterification. But let's draw a little bit more resonance here so we can understand the properties of this molecule there. So if we start with our open shell carbon, we have a positively charged carbon. Now there are two oxygens bonded to that carbocation, so this is not too unstable. It is unstable, it's still an open shell carbon. But there are two places where that carbon can accept electrons. And the first one we've already shown in the mechanism as that resonance structure above, where the OH group oxygen provides electrons. So now we have all closed shell atoms. The positive charge is owned by the oxygen, but still an important and valid resonance structure. Now the OCH3 group, the methoxy group, could also donate its electrons instead of the OH. So we can show that pi bond breaking and a new pi bond forming. And this is another important resonance structure, where again we have all closed shell atoms. And a positive charge on an oxygen, but more importantly, all atoms are closed shell. So in this last structure, again, another valid and important resonance structure, these electrons that are shared between the carbon and this positively charged oxygen can exist in a pi bond and also be owned by that oxygen, so that we have a resonance hybrid that exists in reality. But showing the second resonance structure above in the mechanism helps demonstrate how the reaction is completed, because either way, to form our final product, we have to remove this hydrogen here. And so showing the pi bond between the OH oxygen and the carbon is productive in forming our final product.